Good day, I'm Dr. T and welcome to my office. So today I'd like to talk about chemical reactions, actually getting into doing some chemistry. Okay, so chemical reactions, we are, by the very nature of them, going to be rearranging our atoms, at least to some degree. And to do so, let's bring in some terminology on how we're going to just talk about these guys. So we got a chemical reaction. You got some stuff, and it's going to do some stuff, and it's going to become some stuff. So the starting material, what we start out with, we call those the reactants. Then those are going to react. If we're writing this in an equation, we would put the chemical formula of one reactant, a plus sign, the chemical formula of the next one, a plus sign, the chemical formula of the next one, so on and so forth. Usually it's one or two is normal, but you know, it can be more than one or two. Then is going to be an arrow, and we pronounce the arrow yield, we pronounce the plus signs as and. You know, this and that, but we use a plus sign. And what's going to come after the reaction, our products of the reaction are our products. We're actually not that original in naming things. So yeah, and that's going to look similar to the reactant. So it'd be, you know, chemical plus chemical plus chemical plus chemical. And we would pronounce the plus signs and as well. And this is our core chemical reaction. And depending on what is taking place, this will, you know, give us a clue what's going on and give us some rather important information. So if you look at a chemical reaction, there's two other pieces of information that are quite often on there. For starters, you will see after the chemical formulas quite often a parentheses, letter parentheses. And these letters typically are going to be an S, L, G, or AQ. And these are state symbols. It's saying that this particular chemical is a solid, liquid, gas, or dissolved in water, respectively. This helps us understand a little bit of what's going on and how our reaction typically takes place. Since for a reaction to take place, two chemicals have to literally collide with each other, typically we're going to see reactions in which one or more of the chemicals is either dissolved in the solution, whether it be aqueous or some other solvent, or are a gas. That said, solid-on-solid reactions definitely do happen. They're not as common. They only happen right on the surface where the two rub together, but they are definitely a thing, and they are definitely important. And, well, liquid and liquids, they can mix as well, but liquid reagents are less common than you would think. Another piece of information that's almost always in a chemical equation is going to be a full-size number coming before the chemical formulas. This is a coefficient and describes the ratios of the chemicals involved. So if I have, say, calcium chloride reacting with silver nitrate, I would end up putting a 2 in front of the silver nitrate because I'm going to use 2 formula units of silver nitrate for every 1 formula unit of calcium chloride. I wouldn't put a 1 in front of the calcium chloride because, kind of like the chemical formulas, we don't usually write 1s. But this is giving me a ratio of, you know, how many of these to how many of those. And then those will appear on the products as well. That will give me an understanding of, well, okay, how much of these products, you know, am I going to get out? With these numbers attached, you'll quite often hear this called a balanced chemical equation. And this will have the same number of each atom just shuffled into different spots during your chemical equation. You might see a little bit more information on your chemical equation. Above and below the arrow, we'll quite often put things like reaction conditions, solvents if it's not water, or heat, which is quite often done by putting a triangle. If there's any catalyst, which are chemicals that help speed up reactions, those will go above or below the arrow as well. Now, when it comes to types of reactions, we can broadly break chemical reactions into 4 broad categories. Decomposition reactions are going to start with a single reactant. Due to the reaction conditions, whether it be heat or something else, they're going to break apart, typically producing 2 or more products. Fairly straightforward reaction. Now, the opposite of a decomposition reaction is a synthesis reaction. In this case, once again, due to reaction conditions and the availability of both reactants, 2 compounds will collide into each other and will form a new compound. So 2 or more reactants become a single product, and this is a synthesis reaction. The other 2 are replacement or displacement reactions. You'll see both terms used. They are interchangeable in their meanings. It's kind of an old versus new, US versus UK kind of thing. So in a double replacement reaction, you'll have two reactants, they'll each have, kind of two halves. These are almost always ionic compounds, so I have a cation and an anion, and basically they're just going to swap. And now, boom, you've swapped out cation for anion. A single replacement reaction, quite often, one is coming in as a pair, traditionally cation, anion, and the other one is not. It's usually just a single either element or some form of compound, and only part of it's going to get swapped over, not a full swap. Now, when talking about chemical reactions, I would be amiss to not talk about a overall group of reactions that can be both synthesis, decomposition, or single replacement reactions. And these are the redox reactions. Redox stands for reduction and oxidation. And in these reactions, electrons are transitioning from one atom to another. It may not be a full hard transition, but in many cases it is. With redox reactions, the movement of the electrons is typically going to be a driving force for the chemical reaction. Chemical reactions typically have something that drives them forward, some reason why the reactants want to become the products, although I shouldn't say that they all do. In fact, many of them will reach a balance going back and forth, reactants forming products and products forming reactants. These are what we refer to as the equilibrium reaction. It can be driven forward by preference for the electrons or one of the reagents somehow becoming unable to react and move backwards once it becomes a product. These would be things like gas-forming reactions where the gas evolves off and therefore the product gas cannot become a reagent for the reverse reaction, or a solid-forming reaction where, once again, the solid product can't enter the solution to become a reactant again. But one of the more interesting set is the one where electrons share and move across from one topic to the other. And the last part of chemical reactions I do want to bring up, which you would think would be directly correlated to my previous statement as a reason why a reaction would go one way or the other, but it's not, is that some reactions will release energy, what we call exothermic reactions, exo or exiting and thermic heat, where other reactions will consume energy and will make a solution colder when they're taking place in it. These are called endothermic reactions. Whether or not these are a one-way reaction depends on the conditions, and there are cases where simply changing the temperature can get a reaction to go one way or the other. But it is an important part to keep in mind. Of course, exothermic reactions we've kind of already talked about when we talked about chemical potential energy, because that's exactly what's taking place. In an exothermic reaction, the energy that's stored, it's wrong to say it's stored within the bonds. It's actually energy that is being released by forming new bonds. So you break old bonds. That always takes energy, what we call the activation energy. And then you reassemble your atoms into the new product. And it may just be like a bond that gets broken. It may not be all of them. Usually it's not. If those bonds are more stable and are able to shed more energy in their formation than it took to break the original ones, then you're going to have an exothermic reaction. And thus give off chemical potential energy and turn that into heat and or work. Whereas in an endothermic case, you're going to break the bonds, but you're not going to get as much energy back when you reform new bonds. And in that case, you're taking heat and or work and turning it into chemical potential energy. So with that said, have a wonderful day.